Hi everyone, my name is Kavishavidhanapatran and I'll be presenting our work titled Spectral Geometric Verification, Re-ranking Point Cloud Retrieval for Metric Localization. Metric localization is vital for state estimation in mobile robots. It enables many tasks such as relocalization, for estimating the robot's pose on a given map, loop closure detection for mitigating the accumulation of drift in its land, and also multi-robot map merging. LiDAR-based metric localization in large-scale environments is typically formulated as a hierarchical process of first estimating a coarse-level place candidate and then estimating a 60-degree of freedom transformation using point cloud registration. The first step, known as place recognition, is typically formulated as a retrieval problem by encoding the query point cloud into a compact global descriptor, which can then be used for efficient retrieval over a large database. While this approach has become popular, we note that the best retrieved candidate can sometimes be incorrect, and an incorrect retrieval will hinder the registration and prevent accurate metric localization. For example, for a query point cloud shown in the blue box, the top one candidate shown in the red box appears to be visually similar. However, we see that the top one candidate is actually from a different place. Instead, the correct candidate, shown in green, is retrieved as the second best option. This happens when there are multiple structurally similar places in the database and the network struggles to discriminate between them. Re-ranking can be used to address this failure case by reordering this set of candidates such that the correct candidate be ranked first. The most suitable approach to re-ranking 3D data is geometric verification. As the name implies, geometric verification aims to verify whether the geometry of the query and the retrieved candidate are similar. It will generate a geometric fitness score for each candidate and then re-rank the candidates by sorting them based on this score. The baseline method for checking geometric consistency is to register the query and the candidate using point correspondences and to calculate the inline ratio of the correspondences after registration. This process of pairwise registration of all candidates is inefficient. It prohibits processing a large number of candidates during real-time operation. To address this, we propose a geometric verification method that does not require registration and directly calculates the geometric fitness score. This efficient approach enables re-ranking of a large number of candidates while operating in real time. The calculation of this geometric consistency measure is done by computing the compatibility of the correspondences between the query and the candidate point clouds. In this figure, we see three example correspondences where the green lines indicate correct correspondences and the red line indicates an incorrect correspondence. The compatibility of two correspondences I and j, noted as Mij, is computed by checking the change in relative distances between their points. That is, the change in length of the dotted black lines in the figure. For a correct correspondence, the dotted black lines should remain roughly the same length, and for an incorrect correspondence, they will not. Using this, we can construct a compatibility graph such that the edges between correspondences are weighted by this compatibility score. The adjacency matrix of this graph, for this example, will look something like this. We can observe that the correct green correspondences C1 and C3 have high edge values, and the other pairs of nodes do not. From spectral graph theory, there is an interesting property of this matrix. The leading eigenvector of this matrix, V star, can be used as an indicator vector that estimates the nodes of the main cluster of this graph, where in our application, the main cluster is likely to be the correct correspondences. We see that in V star, the entries of the first and the third place are high, indicating that the main cluster consists of nodes 1 and 3. Finally, we can use this adjacency matrix and its leading eigenvector to get a scalar score, which is the average of the compatibility scores of the main cluster in the graph. In this work, we show how this score can be used as a fitness score for geometric verification-based re-ranking. Here, we see an evaluation of place recognition of different re-ranking methods in terms of recall at one performance after re-ranking. We show the popular baseline method, alpha query expansion, in green, and the best registration-based geometric verification method, ransack GV, in red, and our geometric verification method, Spectral GV, in blue. We first show how rewriting methods which do not utilize geometric verification, such as alpha QV, struggle in the 3D domain. For methods that perform geometric verification, our method performs on par or slightly better than the other options. The main takeaway, however, is the efficiency of our method. While other geometric verification methods shown in red scale linearly with the increasing number of candidates used, our method, shown in blue, maintains an almost constant runtime. This enables the use of geometric verification-based re-ranking in real-time settings. We also show results beyond place recognition for the task of 6 degree of freedom metric localization. First, we show that our method is architecture agnostic. Our method can be used with any metric localization architecture without modification and without retraining of learning-based methods. Also, using our re-ranking method, we are able to obtain performance improvements even for 6 degree of freedom force estimation, setting the current state of the art for metric localization. Finally, we know the Spectral GV is training-free, and it can be used with any pre-trained network and even improves performance of these networks on unseen data. Check out our code base to see if Spectral GV can improve the accuracy of your network. Thank you.